So let's pick up where we left off with applications of Kepler's third law of motion. So we just got through saying if you want to find the mass of a heavenly body, you just got to look at the information of something orbiting it, the period and the radius, and there we have that Kepler's relationship of r cubed over t squared is a constant. So I also want to be able to have us do this for some generic orbits, especially for satellites. And so for number 2, I'm going to look at 2 special derivations. Not difficult, much more simple than the one we just did, but something I expect you to be able to do. So one is deriving equation for the orbital velocity. You did this in the circular motion one for a very simplistic case. I'm going to remind you, this is not the derivation, but let me remind you what you've already done. So if this is the Earth down here, and I want to, actually, now I'm going to draw the Earth, right? The idea was, let's say here is the ground. I can fire something fast enough so it falls around the Earth. Now, we normally want to be outside the atmosphere, so drag is an issue, but our derivation for this was that velocity, orbital velocity, was nothing more than radical gr. Okay? You can go back and look at, I think it's problem number 1 from your centripetal forces homework. So this equation will not work, or was inaccurate, because little g was assumed to be 9.8. But if I'm going to put if I have a planet and I want to put something in orbit around it, I can't assume little g is 9.8 anymore. We should know by now that it's going to decrease because the distance to the planets has decreased measurably. So we need a more general derivation. The good news is it's the same process that you did before. Okay, so if I've got this picture up here of some generic satellite going around a planet, okay, we can ask ourselves, all right, why is it going in a circle? Well, there's something pulling it inwards, and that's, of course, Fg. And Fg is causing a centripetal acceleration. So we can apply the second law. So we can say, all right, our supply force is Fg, and that's got to equal the demand on the force, which is mv squared all over r. And what I'm looking for is orbital velocity here. So there's the v. So all I got to do is calculate f of g. I can't use m little g now because we don't know what the planet is or how far away we are. So we're going to use the universal gravitational equation. That's not hard. So I'm going to write this then as big G, mass of the planet, mass of the satellite, so I can keep track of the masses, divided by how far away we are from squared. I'm just going to go to capital R because I prefer that. Equals, so we got to ask ourselves, what mass are we talking about in this equation? Well, that's the demand on the force. That's the satellite moving, so that's mass of the satellite. The orbital velocity, that's what it measures to squared, all over how far away we are, and that's r. So this simplifies nicely. We can see that the mass of the satellite does not matter. Okay, how fast you have to orbits doesn't matter. And we saw that in the previous equation, radical gr, so that's consistent. And if we solve for v, so I'm going to do it in 2 steps, so I can say v squared, or orbital, and if I cross multiply, that's going to be equal to g, mass of the planet, all over r. Okay, because when I cross multiply this r over to here, that cancels out with just one of the r's there. Okay, so our orbital velocity then is nothing more than g, mass of the planet, all over r, square root of that. Sorry, that got crunched in there. Okay, so I believe that's in the IB reference tables, but you should be able to derive that for a homework or a quiz. It's a simple derivation. And we see then that the orbital velocity is inversely proportional to the r, or the square root of r. So if I go further and further away, you have to fire it at a slower and slower velocity to keep it in orbit. And that should make sense. Okay, the next thing I want to talk about, I got to erase this, is a special application of this. And that's a geosynchronous orbit. Okay, so a geosynchronous orbit is especially important for GPS satellites. And what a geosynchronous means is, geo means Earth, synchronous means in time with. And so these are satellites that orbit the Earth with the same period as the Earth's rotation. In other words, 1 day. In other words, there are certain satellites we want them to have a period of revolution of exactly 1 day. All the other satellites you talk about are generally hours, tens of hours. They don't circle 1 day. We don't really care about their period so much. But for geosynchronous, we want it to be exactly 1 day, which converted to seconds is 86,400. So why would we want that? Well, pretty simple. If a geosynchronous means if it's rotating with the same period as the Earth, it will stay above the same spot on the Earth the entire time. So if I want a network of satellites always above certain spots of the Earth, so we can always pick them up from anywhere we are on the Earth, or at least 2 or 3 of them, for location purposes, that's the point of that. Whereas other ones are just constantly zipping around and could be over different spots of the Earth at different times. So this geosynchronous orbit has this very specific distance. You can only achieve this at one distance because you are setting the period to be 1 day. So to figure out that distance, we just use Kepler's relationship. In other words, from above, the very top, we know that r cubed over t squared equals big G, mass of the planet, in this case the Earth, divided by 4 pi squared. So we're not solving for the mass of the planet. We assume we know this. We are given t because that's the definition. It's a geosynchronous, which means its period is 1 day. We're just going to solve for r. So algebraically, that becomes r cubed equals gm t squared all over 4 pi squared. I strongly suggest you put in the numbers again just to get that practice. When you put in numbers for that, you're going to get 7.5 times 10 to the 22 units. Okay? And that's not the answer though. We got to remember, I almost forgot to do this. This is cubed over here. So in order to get the value of r, I got to take the cube root of this whole thing. And when I do that, I get about 4.2 times 10 to the 7th meters. Okay? Now that distance isn't necessarily going to mean much to you, but let me put it a little bit in perspective. Again, let me just draw a generic Earth. So if we have a generic Earth here, most of the satellites we put up there are essentially right there. They are around 10 to the 6th meters away. In other words, the Earth's radius is about 6 times 10 to the 6th. These are closer to 8, 9, 10 to the 6th. We are talking 10 to the 7th, so we're significantly further away. The moon is way out here, I believe, at 10 to the 8th. Okay, but geosynchronous satellites are way far away compared to other satellites, but not as far as the moon. So the last derivation is a nice one. I won't necessarily expect you to reproduce it, but it's a good application. So imagine we have a planet, an unknown planet, planet X, and we want to know not just its mass, we want to know its density. And the reason we want to know its density, it gives them an idea of what kind of material it's made of. If it's a really low density, like less than 1, maybe it's just a gas planet. If it's a density of 3 or 4, then we know it has rocky minerals on it, water perhaps, etc. So one way you can do that is you can send a probe to that planet, and you can have it orbit it. And in that orbit, you're going to have a period and a distance, where the distance of the orbit is essentially the distance, the radius of the planet. Well, based on that, we can actually get the density of the planet, and it's really just a variation of the mass. Okay, so if you recall, density, which we're going to call, I'll call it d here. No, I'm going to call it rho. Okay, so that's the Greek letter rho is density. You know is mass per unit volume. Okay, so, well, how do we know the mass of the planet? Well, we use the information from the r cubed and t squared. So we know that mass from the previous problems that we did is going to be 4 pi squared r cubed over gt squared. That's the mass. That comes from the problems you did for solving for the mass of the sun and the one above. And then we're going to divide it by volume. Well, what's volume? Well, it's a sphere, so volume is 4/3 pi r cubed, so I'm going to put that in the denominator. I'm going to put it in a different color just to highlight it. So that's 4/3 pi r cubed. And there's our density equation. Okay, well, obviously we want to simplify things. So this is a copy, change, flip scenario. And it's a good one for you to do because you need practice simplifying complex fractions. So I'm going to rewrite the numerator. I'm going to change the denominator by flipping it, making it a multiplication, 1 over, 4/3 pi r cubed. Now that 4/3 might throw you off, but I'll handle that. And so look at that. We see that the r cubes cancel out. Okay. Let's see. Now 4 here cancels out the 4 there. The 1 over 1/3 becomes a 3. So that leaves us in the numerator, and a pi here and a pi there cancel. So we left with 3 pi all over gt squared. And so that satellite can measure the period, square it, multiply it by the universal gravitational constant, and then use the 3 pi. You've got the density of that planet. That's pretty cool. So from here on are just practice problems. You're going to use the equations that are derived in the previous page. So this is just an orbital velocity. On a quiz, you wouldn't necessarily have that equation in front of you, but maybe you want to derive that for yourself here. I strongly suggest you do that. Okay, and so you're going to do it for Venus. So you're going to use the sun's mass from the problem you solved earlier, and then you're going to use Venus's orbital distance from the chart on page 1. And don't forget to include that times 10 to the 9th or whatever it is for that distance. Okay, how does the orbital velocity change? I want you to explain. You reference an equation there. Calculate the average density of the Earth. Use the derived equation I just did. You don't have to re-derive it. And assuming a period, I give you that. So, and then why is it important to be very close? I'll let you try to work that out. And then number 6, I think, goes back to the original equation of Kepler. So this is a good one. I like that one. And the answers are there on the right. Okay, good luck with that.